Now you're unmuted.
Woo, I'm unmuted.
And then just click on one of the Chrome tabs and it'll have the presenter view.
Okay, mine is in
This one?
Which one says presenter view?
This one.
Yeah.
Cool. Wait, this isn't updated. So I just got rid of that. Can I close this in the opener?
Yeah, you should be able to. Go over to the right screen. I drag it to the right. Click and press enter, or exit, I mean. Press exit. Or escape, sorry.
I feel like that's a no.
Yeah. Yes, it's a no. Or the right screen. Escape.
Oh, okay.
And then I guess refresh.
I think it's been used correctly. I got to refresh.
And
Okay.
back to your top one.
Now I see.
Click on the arrow under present. Click on presenter view. Drag that screen over to the left. That way you have it right there. You can make it big.
Cool.
And then you can full screen that one. Go put your mouse towards the bottom of the screen, and it'll bring up, yeah.
Sorry, I'm really looking at.
And then you can like put your mouse back to the left screen so you can control the presenter view.
How many people do we have now?
7.
7. Wow, thank you, 7 of you. We're going to go ahead and start here.
Oh, sorry.
We're going to go ahead and start here. So this is GY 252 midterm review. I am Miles. If I'm not your instructor, don't freak out. It's okay. You're still in the right spot. We're going to go and get started here. And surprise, surprise, we're going to start with Lab 1 Map Essentials. So, for your midterm, you need to know the 2 types of maps, which are reference map, which can be used for finding a specific location, and they're good for navigation. So if you need to go find Pete Matthews Coliseum, you're going to use a reference map. And then we have our thematic maps, which is used to show specific data. They're colorful and dynamic. That'd be like if you wanted to map all NCAA schools in the Southeast or whatever, sports. So that's the theme here. So yes, so this would be a reference map. This would be if you wanted to find someone who lives in the village and you're all the way over here on campus. So you use a navigation. This one would be if you were navigating again specific streets. So again, if we go back to our slide and we think about it, so our reference, are we referencing, so are we finding something, or is there a theme here? That's our thematic. So again, here's our reference map, so we'd be using it to reference to find something. And let's talk about, this is a political map, so that means it's a thematic, because it's political. So it's showing different things. So, oh wait, no, that's thematic. Yeah, that's reference, my bad. This is a reference map. Okay, so now let's talk about our thematic maps. Here, the theme would be tornado damage. So we have our map key legend over here showing us, hey, this has been damaged, that's been damaged, this is very damaged, or unknown or undamaged. So the theme here again would be damage. So let's look at some other thematic maps. Here the theme seems to be, this is moisture regimens. So this would be talking about hydrology. So water is our theme here. This appears to, this is a percent of 65 years and older. So our theme here of Texas, so even though it's showing all the little breakdowns of counties in Texas, it is not a reference because it has colors, it's got a theme, it's showing us specific data. So, also in Lab 1 is scale. So scale is defined as the ratio of the actual area of the Earth's surface to map space. So if you have a map in your manual, go ahead and flip to it and look at the scale. It's usually like a scale bar or something like that. So when we talk about scale, there's two types. There's a large scale and there's a small scale. The way I like to explain it is if you're zooming in or you're zooming out. So a small scale is when you zoom in, a large scale shows a smaller area and has more details. A small scale shows a larger area and has less details. So with the zoom in, zoom out. If you have a picture and you zoom in really close, it's now showing it's showing a smaller area but has lots of details. So if you zoom in on a picture of a person, maybe you can see their freckles, you can see their glasses. And then if you're going to zoom out, which would be to a small scale, maybe you see they're standing next to another person. So, but you don't see their freckles. Maybe their glasses are really the thin ones, so you don't see them. But you can see there's 2 or 3 people. Maybe you see the color of their hair, which you didn't see when you zoomed it in. So that's our scales. Here, so if you want to take a moment, pause this. Even though it's a live stream, you can pause it. And try to identify which one's which. Give you guys a second. So yes, here's our large scale and here's our small scale. So here we are, we've zoomed in really close into Jacksonville and we can see all the different areas. We can see a road here, we can see a little bit of the outlines of some areas. This is Trustee Circle right here. You can see Martin Hall if you're an in-person student. We're going to be to Martin Hall. We're going to be over here. There. So yes, we've zoomed in, we can see lots of details. Large scale. So then we have our small scale. We've zoomed out really far. And we might not even know where Jacksonville is. But since I'm a geographer, I do know where it is. It's over here. So yes, let's look at another example. This is Atlanta. So take a moment, pause your stream, or pause this video if you're watching it later. How dare you not watch it live? So what do we have here? This is very zoomed out, and this one's very zoomed in. So take a moment, think about it. Small scale, large scale. So yes, small scale, we can see not a whole lot. we know this is Atlanta. We can see some of the bigger interstates. We can see this foresty area over here, but we see a lot of it. So then we have our large scale. So we can see interstates, we can see the outlines of some buildings. Looks like Spaghetti Junction over here. There's lots of things going on, lots of roadways, lots of building blocks. So we've zoomed in so we can see a larger scale. Okay, so here again is another example. So let's talk about the anatomy of a map. If we were to dissect a map, what would be the 6 things we want to look for? So, title. I'm not jumping again. It's way up there. This is Riga, Latvia, which is the Old Town District. So that is our title. That is what this map is showing us. What are we looking at? We have our symbols. So, there's a symbol here. What does this symbol mean? I don't know. Oh, it means a Capitol building. Legend. This whole thing over here is our legend. It's telling us, hey, these are the important things that we want to look at. For example, a Capitol building. But it also tells us, hey, this over here is a major road. This is water. This green area, it's a park. So that's our legend. And then our scale is down here. It's pretty small to read. I do believe it's less than actually it might be this might be a mile. That's our scale here. Then our compass arrow, or compass rose up here, and that's showing north. Okay, and then our grid or graticule, which is 6. There's these little squares, and we're going to talk about them more in future or in the next section. So don't worry about them too much for Map Essentials. But it's basically showing us, hey, this square is the same amount of area as this square, that square, that one. All the squares mean the same area. So yes, those are anatomies of a map. If you need to pause this and like really think about numbers going to places, you can do so now. So, speaking of scale, representative fraction, RF, is 1 unit of an object placed on the map is equal to X amount of those same units in the actual area of the Earth's surface shown on the map. So the examples we like to use is 1 unit of bananas is equal to the same on the map space to 12,000 those bananas. So, or is it right? Is it right? So, one banana placed on the map is equal to 12,000 bananas in the actual area. So yeah. You can also use, you could use feet, you can use miles, you can use kilometers, you can use shoes, iPhones, you can use whatever you want as long as it's the same on both sides. So, we also look at maps, sometimes we'll see a ratio. It can be read as 1 to 17,000, or 1 in 17, or 1 in 1 to 17,000 miles. So don't get too caught up in those. It's just telling you, hey, this is the ratio of that. Okay, then we're gonna let Emily go to lab 2.
Okay. Hello, everyone.
Do you want me to help you write first?
Sure, you want to test that? Yeah. Okay.
Sorry. It looks like there's only a pointer option on here, so I'm not sure.
Can I write on this? Can the camera see it?
Let's see. A bit, yeah. We'll probably have, we can zoom in the camera once we
When we get there.
get there.
Okay.
There you go.
Okay, let's talk about lab 2, latitude and longitude. So, like Miles was just talking about with the grid or the graticule, that is basically just the big coordinate system is like a big grid laid over on top of the Earth. It is invisible though, we can't see the grid lines. It's just imaginary lines that we've come up with, and it's a universal system, coordinate system that they use all over the world. Every single country is going to use this coordinate system. It's not like metric or anything where different countries use different things. Everybody uses this coordinate system so that when you give out coordinates, anybody in the country is going to know exactly the location you're talking about. So, starting with latitude. Latitude is our lines that measure north and south. And so, these lines are horizontal lines, but they measure north and south. And so you see right in the middle is our equator at 0. The equator is our longest line of latitude because it's at the thickest point of the Earth. The Earth is thickest right in the center, so the equator is the longest line of latitude. So our equator, like I said, is also 0 degrees. And then as you go north, you go all the way up to the North Pole at 90 degrees, and then you go south all the way to the South Pole at 90 degrees south at the bottom. Another thing about latitude, we just talked about the equator and how it's the longest line. You can see right here that the equator is the longest line. That's where the Earth is thickest. And then when you get all the way down to the poles, it's just a point. It's not a line anymore. So if it was 89 degrees, it would be a tiny little line, and then it gets all the way down into a point. Then for longitude, our lines of longitude measure east and west, but they are vertical lines like this, but they go east and west. And so we talked about the equator for latitude, but the longitude version of the equator is known as the prime meridian. So the prime meridian is right here at 0 degrees, and it runs through Greenwich, England. They decided in, I think, 1884 that the prime meridian was going to run through Greenwich, England. And when I say they, I'm just talking about a big conference of a bunch of scientists. They're like, we're going to put the prime meridian through Greenwich, England, and because we say so. So if the longitude starts at 0 with the prime meridian, it wraps all the way around the world to the other side. So it goes all the way around to 180 degrees. And so we talked about latitude. The highest degree of latitude goes up to 90, but the highest degree of longitude is 180. So it goes all the way to 180 east, all the way over to 180 west. We also talked about how latitude, there are different lengths. For longitude, they're all the same length because every single line of longitude goes from the North Pole to the South Pole, so each one of them is the same length. So then we talked about the prime meridian being 0 degrees, and it wraps around and meets at the other side of the international date line, which is 180 degrees. Now right here, this black line is for time zones. That's not the international date line, but that's where the international date line would be, in between Alaska and Russia. But this jagged black line is just for time zones, but the international date line itself is just a straight line of longitude. And so all these different lines that we're talking about, the equator and the prime meridian, they divide the world into hemispheres. The equator divides the world into the northern hemisphere and the southern hemisphere, and our equator runs through the center right here. And then our prime meridian and the international date line divide the world into an eastern and western hemisphere. And so here's a map. We're going to practice finding different coordinates. We're going to practice finding different coordinates with this map, looking at the cities. So we see we have New York. We're going to find the coordinates of New York first. So first thing, we're always going to look for the latitude first. Always latitude first. So looking at New York, the latitude is in between 30 and 45. So just eyeballing it, guesstimating here, I'm going to say the latitude for New York is 41 degrees north. So that's not quite 45 up there, but I would say 41. And then for longitude, here's New York. It's right off of this 75-degree west line, but it's just under it. So instead of 75, I'm going to say 74 degrees west. So the coordinates for New York are 41 degrees north and 74 degrees west. Another example is Cairo, Egypt. Here's Cairo over here. And so we're going to find the latitude first. So latitude is our north or south. And so it looks like it's just on that 30-degree north line. So for Cairo, I'm going to say the latitude is 30 degrees north. For longitude, it looks like it's just off of this 30-degree east line. It's a little bit forward, so I'm going to say it's 31 degrees east. So Cairo's coordinates is 30 degrees north and 31 or 32 degrees east. And then let's say if we actually get coordinates and we have to find whatever country it's talking about. So for example, let's look at the coordinates 30 degrees south and 135 degrees east. So 30 degrees south, say those are north, here's our south, here's 30 degrees south, and it's 135 degrees east. So here's west, east is over here, going all the way over to 135 is actually the very edge of the map. So if we're looking at 30 degrees south and 135 degrees longitude, it's right here in Australia. So those coordinates refer to Australia. And then one more example, let's say we have the coordinates 0 degrees and 60 degrees west. So looking at 0 degrees for our latitude, 0 degrees is the equator. So whatever country we're looking for is going to be on the equator. The longitude is 60 degrees west. So east over there, west over here. Here's 60 degrees west on the equator. That's going to be Brazil. So for those coordinates, the country is going to be Brazil. So that's how you find latitude and longitude coordinates, or find the country that you're looking for. Just use this like a grid, and then just find your points. So we also learned how to convert coordinates. You can either have them as degrees, minutes, and seconds, and then you can also convert them into decimal degrees. Or you can go from decimal degrees into degrees, minutes, and seconds. So we're going to do some practice problems to go over this real quick. Okay. Just right over here.
Yeah, we might have to cut on a light to be able to see your writing.
Okay.
Let me double check.
Oh.
Let's move the owl.
Yeah, it's really hard to see. Can we turn this off for a second?
Maybe.
Okay. So we're gonna start with converting degrees, minutes, and seconds into decimal degrees. So in order to do that, we're gonna start and take we need to convert our seconds into minutes.
Is that better?
It looks better, but I think I need a darker marker.
Well, I can run downstairs and then get one if none of those are better.
I don't know. Can they comment and see if can they see it?
I can't see it
I
either.
can't see it.
I'll run downstairs and get a smaller or a better marker maybe.
Or could you just open up like a Google Draw or in MS Paint?
We can do it.
I can go to MS Paint or we can just talk through it.
We can share a different screen, hold on. Let me, or this back small. Oh, I need to bring on the projector. I'll bring it over to the screen where you can see it.
So now what?
Well, now we can see the Google Draw.
I just draw in here with the mouse?
Let me give you like an
See, that's
actual
gonna be
mouse.
That's not gonna look good.
I'll put it in here. Do you want a mouse there too?
Okay, awesome.
I'm able to work without a mouse pad.
Here we go. There we go. Okay, everybody's still with me. We are converting degrees, minutes, and seconds, and we're trying to convert it into a decimal. So how do I draw in here?
Click. Wait.
Okay. Thank you. Okay. Is there not any other way we can do this? There's no way. Like, look at this. 27. Oh my God. Okay, let's just skip the coordinate conversions right now and we'll come back to it.
You got a better idea?
I don't have a better idea, but we can skip
You
it.
could type it.
Here, I'm gonna talk through it. You wanna do that? Okay, everybody on your scratch paper at home, just write down what I'm speaking. So we're converting degrees, minutes, and seconds into decimal degrees. And what we're gonna do is start with our seconds, and we need to convert those seconds into minutes. There's 60 minutes in a degree, and there's 60 seconds in 1 minute. And so 60 is the magic number here. That's the number we're going to be using to convert and do all these conversions. So to convert our seconds into minutes, we're going to use 60. So we're going to do 45.5, and we're going to divide it by 60. So when we divide 45.5 by 60, it's going to give us a decimal. That decimal is 0.7583. And so all that is 45.5 converted into minutes. So we're gonna take those minutes that we just converted and add it back to the original minutes, which is 42. So taking 42, adding that decimal, it's gonna be 42.7583. So now we just combined our seconds into the minutes, and we need to convert our minutes now into degrees. So all we're gonna do again is just divide by 60, because that's the magic number. So we have 42.7583 divided by 60, and that converts all of that into degrees for our final answer. So when you divide that, it's going to give you a decimal 0.7126, but all that is the degrees, and so you add that back to the original degrees, which is 27, and so the final answer is 27.7126. And then don't forget your direction, and it's north. So all we did there was divide by 60. We're going to do the same thing for the longitude here. All we're going to do is start with the seconds, which is 29.5. Start with those seconds. We need to convert them into minutes. So we're going to divide by 60. 29.5 divided by 60 gives us the decimal 0.49167. And so we're going to take that decimal, which we just created, and so that's our minutes, our new minutes that we created. We're going to add that to the original minutes, which is 19. So now we have 19.49167, and we need to convert that to degrees, so we divide by 60. And so when I divide all of that by 60, I get the decimal 0.32486. And then all the last step that's left is to add it to the original degrees, which is 85, and it gets our final answer, 85.32486. So that's how we convert degrees, minutes, seconds into decimals. We're dividing by 60. And so there's a lot of times confusion of whether you divide by 60 or multiply. A good way to remember here is when you're going from minutes and seconds, you see we have all these whole numbers, 27, 42, 45.5, all these big numbers. And so when you're trying to create a decimal, you're going to divide. So that's how you know you're going to be dividing here, because you want that 45.5 to turn into a little tiny decimal, because that's what we're trying to go for here. Whereas in the next conversion, when you're going from decimal degrees to degrees, minutes, and seconds, we're going to be multiplying, because we're trying to make those whole numbers. You know, we want those big numbers. So let's do this practice problem. So converting decimal degrees into degrees, minutes, and seconds. So what we're going to do here is take the decimal, and we need to convert it into the minutes and seconds, because we already have the degrees. The degrees here is 34 and 119. We need to turn that decimal into minutes and seconds. So leave the decimal alone. Leave the degree alone. Leave that 34 where it is. The 34 is going to be the same in the final answer. So we're just going to take the decimal 0.437287. So just take that decimal, and we're going to multiply by 60. So 0.437287 times 60 is going to give us 26.23722. So 26.23722, we just converted that decimal into minutes. So all we want here though is that whole number 26. So take out the 26, because that's going to be our minutes, and we need to convert everything behind the decimal point into our seconds. So far, our coordinate is 34 degrees and 26 minutes. We need to find the seconds. So we're going to take that decimal, that 0.23722, we're going to multiply by 60, and that's going to give us our seconds, which is 14.2332. But all we need is the 14. We only need that whole number at the beginning. So for our final answer, for degrees, minutes, and seconds, it's going to be 34 degrees, 26 minutes, and 14 seconds north. Don't forget the direction. So all we did here is multiply by 60, and then you just take out what's before the decimal point. So let's do it again for the longitude. The 119 stays exactly the same. The degree is going to be the same from the start to the end. all we're working with is what's behind the decimal point. So we want the 0.713819, and we're gonna multiply that by 60. So 0.713819 times 60, that's gonna give us 42.82914. So what we just did there was calculate it or convert it into minutes. So we're gonna take that 42 as our minute answer, and all we're gonna work with now is what's behind the decimal point. So that 0.82914, we're gonna multiply that by 60, and that's gonna give us our seconds. So when we multiply 0.82914 times 60, it's going to give us 49.7484. But all we care about is the 49. We don't need anything behind the decimal point anymore. So for our final answer, it would be 119 degrees, 42 minutes, and 49 seconds west. Don't forget direction. So all we did there was multiply by 60. We're only multiplying what's behind the decimal point because each time that whole number is going to become part of our answer. So that's everything for lab 2. Sorry we didn't get to work through the equations like actually on the board together. If you have more questions about that, please email one of your lab instructors and we'll be happy to help you. Sorry we couldn't get the technology to work today, but definitely email us if you have questions or you're confused about that. But moving into lab 3, the atmosphere. So we just talked about, can I bring this back up here? Okay. So for the atmosphere, you know, in the last lab, lab 2, longitude and latitude, we talked about this invisible grid over the Earth's surface. So now we're going to talk about the invisible atmosphere that's also over the Earth's surface. So when we talk about atmosphere, we're mainly talking about the 5 layers and their characteristics, right? So the atmosphere is the ocean of air which surrounds us from the Earth's surface and stretches into space. So it's all around us. Every time we breathe, we're using our atmosphere. And then there's 5 layers, and they're all separated by unique temperature characteristics. So their characteristics are just based off of how much energy they absorb from the sun. So remember, these layers are divided by the temperatures that they basically absorb from the sun, all that radiation they're absorbing. And then we also know that for the atmosphere, there's 2 types of gas. We have permanent gases and we have variable gases. Remember our permanent gases, 78% nitrogen, 21% oxygen, and 0.93% argon. Those are our 3 permanent gases, nitrogen, oxygen, and argon. And then we have our variable gases, which again, they're variable, so they vary, and they're not always stable as the others. So we have water vapor, carbon dioxide, ozone, and then there's also particulates, which are just little dust particles floating around. It's not gases, but they're just all the little matter and dust particles floating around the atmosphere, and there's enough of it to make up a tiny, tiny percent of the atmosphere. So, like talking about the different layers themselves, we're going to start with the troposphere. Troposphere is the first layer. It's the one that we live in. It's closest to the ground, and it only goes up to about 10 kilometers or about, I think, 6 miles off the ground. So the troposphere, again, is where we live, and so this is where all of the weather is going to happen, because a lot of water vapor is in the troposphere, and because of this water vapor, that's what's going to cause rain, clouds, all the precipitation and storms and everything, the humidity, that's from the water vapor in the troposphere. So, and then you also remember we filled out this temperature line before. So this red line is our temperature line. It's going to mark those temperature characteristics for our layers. Remember, those characteristics come from how much energy it absorbs from the sun. But for the troposphere is not really absorbing any energy. And so that's why in the troposphere, the temperature decreases as you increase in altitude. So as we're increasing in altitude and going up, the temperature is decreasing. So that's important to know about the troposphere, is that as you increase in altitude, temperature is decreasing. Okay. I'm sorry, I don't know. I just tapped the screen. Okay, next layer is the stratosphere. The stratosphere is going to be a little bit bigger than the troposphere, and within the stratosphere it's going to have the ozone layer. And then one thing to point out, in between each of these layers is going to be a pause, or like a buffer zone. Think of it as just a little bit of space in between each layer for that temperature jump to happen, to kind of give it a little buffer zone to get to the next layer. And so this one is called the tropopause because it's right above the troposphere. The next one is going to be the stratopause, so whatever is below it, that's what it's going to be, tropopause, stratopause, and then it keeps going. But some characteristics about the stratosphere, some things to point out. We talked about the ozone layer. We know that ozone absorbs a lot of energy from the sun. It absorbs a lot of radiation because all that ozone is absorbing all of those harmful ultraviolet rays. And so if it wasn't absorbing those rays, they would be hitting us and they cause skin cancer. All of those ultraviolet rays can kill crops and plants and everything. It can kill plankton in the ocean, all these important things in our ecosystem. So it's really important that we have this ozone layer to protect us from the ultraviolet rays from the sun. And then looking at our temperature line, you see it starts to go back up. So in the troposphere, it was decreasing as we go up in altitude. For the stratosphere, the temperature is increasing as the altitude increases. So double increasing here. Altitude and temperature are both increasing. And that's because of the ozone layer. Because the ozone layer absorbs all of those energy rays from the sun, it's making all of that heat and radiation cause the temperature to go up. All right, next layer is the mesosphere, and it's separated by the stratopause just to give that temperature buffer a little time to change. And some things about the mesosphere, not a lot happens in this layer. The main thing to point out about the mesosphere is that this is where meteors and asteroids and stuff start coming into the atmosphere and they start burning up on impact. So that's going to be in the mesosphere. When you're watching TV or something and you see asteroids and meteors come in, it'll be burning up in this layer. So then our next layer is the thermosphere. It's divided by the mesopause, just to give it a little space to change. And then the thermosphere has a bunch of different things inside of it. So how the ozone layer is inside of the stratosphere. Same thing, the ionosphere is within the thermosphere. So our ionosphere, if y'all remember what an ion is, it's a charged particle. And so an ionosphere is just made up of a bunch of ions, all those charged particles, and it's very, very small. The ionosphere, I think, it makes up about 0.1% of the atmosphere. So super, super small. It's too small to have its own layer, so it's within the thermosphere. And so why we talk about the ionosphere is because it's what we use to make long-distance radio communication possible. So we send up radio waves, they hit the charged particles, they come back down, and so that's why it's important, that's why we're mentioning it. And then one more thing to mention is the auroras, or otherwise known as the northern lights. They're going to be located at this altitude in the thermosphere. So just to give you an idea, if you see the northern lights, they're way, way, way up in the sky, all the way up in the thermosphere. And then something interesting to point out here, looking at our temperature line, you see it skyrockets back up. And so that's because it's going to be a lot closer to the sun here. And so the sun is going to be hitting this layer first, and it's going to be absorbing all of that radiation and energy first. So it's going to be way, way hotter. So looking at our temperature line, we see it decreases, increases, decreases, and then goes all the way up and increases. So that's how our temperature line works. That's why we have these layers classified by their temperature characteristics. You can see how different they are just by their temperatures. Okay, very last layer that we're going to talk about is the exosphere. It is the outer layer, the edge, that's why it's called exo. So all it is just the thin part around the atmosphere. This is where atoms and molecules, if they get all the way up there, gravity's really, really weak, and so they're going to start floating into space. And so all these atoms and molecules are floating in space, and we'll never see them again. They're gone. So those are all of our different layers, but let's talk specifically about the ozone layer because it is so important to us and just the way that we live and everything. So we talked about how it absorbs all those ultraviolet rays from the sun, and if it didn't do that, you know, we could get skin cancer, we would lose our crops and our food and everything. And so we consider the ozone layer in the stratosphere very beneficial to humans, very important. And so you might have heard about the hole in the ozone layer, and so that was caused by chlorofluorocarbons, CFCs. These chlorofluorocarbons are being released by car emissions and different factories, things like that, are releasing these chlorofluorocarbons, and it's breaking up the ozone. It's created this hole. And so, again, that's going to be really bad because we need ozone to protect us, and so we want to make sure we're not releasing these CFCs. But another thing is if ozone is in the stratosphere, it's considered beneficial, it's good, it's helping us. Anytime ozone is in the troposphere, say it comes down to the troposphere where we are, it's going to be considered an air pollutant, just because we can't breathe ozone. Ozone is 3 oxygen molecules, whereas we breathe O2, which is just 2 oxygen molecules. And so because ozone has that extra oxygen molecule, it's going to be a pollutant for us to breathe. It's not going to be good. And so how we measure air pollutants is with the air quality index. It's going to measure ozone. It's going to measure any other air pollutants. It also measures the particulates in the air. If there's too many dust particles, that's also really bad for your breathing. So it's going to measure all these different things. So here's the air quality index. It's divided into how hazardous the air is to breathe. And so green at the top, it's going to be good. The air quality is great, nothing to worry about. And then as you get lower and lower, it's going to get really, really worse. And so anything orange and below is considered an ozone alert day. So if it goes into a value 100 or more, they're going to declare an ozone alert, and they're going to tell people if you have any health problems or something, you might need to stay inside, try and stay away from outside air, because on this particular day, it's a little dangerous for you. And then you get all the way to the bottom. Anything 300 and higher is super hazardous. This is almost like apocalyptic air quality, so super, super bad for you. Everybody's going to be affected by this. Where in some of the other categories, it's going to be people with health problems are going to be affected, but when you get down to the bottom here, everybody's going to be affected. So that is it for the atmosphere. Again, if you have any questions, please ask your lab instructor. We're going to go over into lab 4 now.
Let's talk about Earth and Sun relations, and if they get along or not. So, let's talk about first the aphelion and perihelion. So when the Earth is closest to the Sun, that is the perihelion. It's pretty close. And there's the aphelion, because it's far away. That's how I tell my students sometimes. So when we talk about the Sun's rotation, you have the Earth and the Sun in the middle, and the Earth is going around. So when it's close, which is 91.5 miles, perihelion. When it goes around, it's a little bit farther away now. It's 94.5 miles, and that's your aphelion. So during those times, there's the solstice. So when the Earth is tilting at the maximum, we call this a solstice. So it doesn't tilt more than, I think, 23.5. That's its maximum tilt. There's the summer solstice, which is June 21st. So this is when the sunlight is most reaching, the most sunlight is reaching the northern hemisphere, and the day the least amount of sunlight is reaching the southern hemisphere. And then we have our winter solstice, which happens December 21st. This is the day the least amount of sunlight reaches the northern hemisphere, and therefore the most amount of sunlight is reaching the southern hemisphere. So you got to flip those around depending on the date in the solstice, the hemisphere. So then, after our solstices, we want to talk about our equinoxes. So equinox is when the Earth is tilted at 0 degrees. So it's like this. So that means all the Earth is facing, it's all getting about relatively the same as it's going around. So if it's straight up and down, it's when you have an equinox. And there's the vernal equinox, which is March 21st, and there's the autumnal equinox, which is September 21st. So there are equinoxes. So remember, it's exactly like this. That's going to be equinox. So let's talk about our tropics and our circles. So I think everyone's probably heard of the lines of latitude that mark the fullest extent of the sunlight directly received. So let's talk about Tropic of Cancer. This one's going to be up in the north. See if I can find it real quick. Just label it on here. Here, yeah. So our Tropic of Cancer is going to be up through here. I'm sure all you can see it from here. But we know it's in the north, so it's going to be 23.5 degrees north. And then on the opposite of that, it's going to be a Tropic of Capricorn, which is 23.5 degrees south. So then we're going to have our circles. So up in the north, we're going to have our Arctic Circle, which means the Antarctic one is probably going to be down here in the south with the Antarctica. Okay? Those are at 66.5 degrees north and 66.5 degrees south. So those are circles. So now we're going to talk about solar angle. Oh, unless there's any questions. Okay? Let's talk about solar angle.
Right. Hello students, we're going to talk about solar angle. Alright, so let's move on to, okay, so we're going to have to first talk about declination. Declination is the angle at which Earth receives light from the sun. So we know that Earth tilts on its axis, right, 23.5 degrees. That means the light that it receives from the sun, you will have areas that will receive more light than others during the day. So higher declinations, right, mean more direct light, which means more daylight. So lower declinations mean less direct light, meaning less daylight. So how would you find a declination? Well, to do that, you would need an analemma or an analemma. You can say it both ways. So the declination of the sun is visualized in this diagram called the analemma, and what this does is if you were to go outside at the same time every day and chart the position of the sun in the sky, you would see that it would make this kind of lopsided figure 8, right? So as we go around the sun throughout the year, okay? And you can see that this diagram has 2 axes listed. So the one is the actual declination of the sun, and the other is where it is on the equator compared to the equator. Okay, and you will see that the equator is actually, it'll be right here. Okay, so right in the middle of the analemma. All right, so how do we calculate the solar angle? Listen, don't be afraid of the math. It's really not that bad. All you have to do is be able to figure out 2 pieces of information. So, as you will see, you have the solar angle, which we use as SA, right, equals 90, which is the angle at which we are using to determine the angle of the sun. And then you get like a whole mess, right? So here's how we're going to break this down. So you take the parentheses, okay, and you're going to have the absolute value. So absolute value means that regardless of whether your product from what is inside the parentheses is positive or negative, you are always going to, it will always be a positive number regardless. and you will have the lambda, L, lambda for location, L, location, lambda, L, location, okay? All right, but then you will have the delta, which is the declination, okay? So D for declination. All right, so your location will be where you are, or what location you are trying to find the declination for, or the solar angle for. So what you're going to do is here in Jacksonville, we're at about 34 degrees-ish. There's an ish there, but we're going to do 34 degrees for the purposes of our what we're doing here. But then you will have the declination. Well, how do you figure out the declination? Well, let's take a step backwards a second. And we go to the NLM. So you'll bring this up, and you will see where are we throughout the year. So what you will do is right now you can see that it is the end of February. So we are somewhere, let's see, around right here. Okay, but what you will do is you will chart where that location is on the analemma and go over there and find how many degrees it is. So you would see it's roughly somewhere between 10 and 8 degrees, so you could say 9, right? So your values for lambda would be our location, which is 34 degrees, and then you have a plus or minus the delta, which would be 9 degrees. Okay? So how do you determine whether you are using a plus or a minus? Well, if the latitude and declination are in the same hemisphere, you subtract. If the latitude and declination are in different hemispheres, you add. So, what we know, going back to the analemma for a second, you're going to come back to this quite a bit when you take your test if you have to figure this out, is you will see that where we are right now in February, we are actually below the equator. We are in different hemispheres, which means you will add. But as the year goes on, that will change. So what will happen is in March, we will reach an equinox, right? Where the Earth, equinox, means equal, right? So we each get the same amount of sunlight, regardless of latitude. That will change, and we will have more sunlight in the northern hemisphere, meaning that you will subtract. All right, so let's move forward. I think there are some examples of this. So, yes, we have some solar angle examples. So we have what is the solar angle for Jacksonville, Alabama on November 15th. Well, let's take this backwards. You know that we have Jacksonville's location, which is 34 degrees, right? But then we have to go to the analemma and say, well, on November 15th, where are we? So again, you guys are probably going to get tired of this, but we're going to keep going back to it. So November 15th, you go and you find it, and you see that is somewhere down towards the bottom of the analemma, right? So it is about at 19 degrees. So when you set up that equation, you would have your solar angle equals 90 degrees minus, and be sure to put your parentheses and your absolute value. So the 34 degrees plus, because we are in a different hemisphere, okay, for that one, and it would be what was that, 20, where were we at there? 19 degrees. All right, so I believe it steps you, yes, there we go, or it does subtract. But, all right, so I had it backwards. Do be like that. So also, I advise you to take this problem step by step. Take this problem step by step. Set it up, and don't just immediately rush for the answer. Take it procedurally. Set up the equation, and then move down as it does here. Okay? Solve it step by step to find the answer. Okay. But let's do another one. So solar angle for Jacksonville on April 25th. So we have 34 degrees. Back to the analemma, right? So you see in April, so go around and find where it is. Mark that location on your analemma, and we're just going to give you a minute here to, okay. And you should come out to, after setting it up, you should come out to 44 degrees. All right. So there's one last thing. Once we have that, once we have the solar angle, we talk about solar intensity. So let's say you take a flashlight and you shine it against a wall, right? And if you shine it directly at that wall, you will have a nice kind of circular, or whichever shape your flashlight happens to take, nice circular pattern on the wall, right? But if you tilt that flashlight up and down, you will see that the intensity of the light on the wall will change, right? So that is also the way that our sun reflects light onto our planet. So what you're going to do is, after figuring out the solar angle, you're going to go to this chart. I assume this will be furnished on your midterm. And what you will do is you will go to the solar angle, and on the y-axis, okay, right here, you will have the tens place. So if your solar angle is 44 degrees, let's say 44, right? You will find the 40 degrees here, okay? And then you will go over on your x-axis to the 4, right? So it would be 69.5. That would be your intensity, your solar intensity. All right. Okay. And that is it for your midterm review. Thank you for attending. And if you have any questions, please direct them to your instructors. And good luck on your midterm.